Chapter 6, Kinetic Energy and Work. Samples. Sample. A uniform chain of length L is put on a horizontal table with coefficient of kinetic energy mu k. Originally, part of its length A is held down vertically at the edge of the table, as shown in the figure. If the chain is initially at rest, find its speed when it is just left the table. This end is at this end, just left the table. This is a pretty hard question because every moment, everything changes. We look at the forces acting on the chain. One is friction force, which depends on the length of this chain. Also, we have gravitational force, which depends on the length on this part held vertically, which changes all the time. So the motivation gets bigger and bigger, the friction gets smaller and smaller while it's falling down. What we do, so we take a small section of movement in the middle. For example, in the middle, this length is just x. X can change from A to L. And then the chain on the table is L minus x. The friction is equal to mu and normal force. In this case, the normal force equal to the weight of this chain on the table. The weight on the table is the length multiplied by its weight density. Total weight divided by total length, the weight density, the length. And look at this gravitational force. It depends on the part of chain this way. And this is x multiplied by the weight density, total weight by total length. We want to find the velocity when it just leaves the table. What we do, we have to use the word kinetic energy theorem. If we can find the total work done by these two forces on the chain at the end situation, and we can find the delta K. So we can find the V. So what we do, let's see that. When we move a little bit dx downward, okay, and the work done by the friction is F dx. F equal to this one, mu k, length density, weight density. And we see the work done by the gravitational force is x dx. X, the weight of x dx. Now, we want to find the total work done by these two forces when it's moved. What we do, let's see. At this moment, we move dx, the work done on this chain by these two forces are this one. If we put them together and exchanges, we have a lot of dx, we'll put them together, sigma. Actually, we do the integration. We get the total work done. And this total work done equal to delta K, we can find the final velocity. Now, we put this inside. dF equal to x mg over L dx. dWF equal to minus mu k Lk. Why is it minus? Because F is go this one, dx go this way. They are opposite. Cosine 180 is minus 1. So we do the decreasing in a very small change. From where to where? The x is from A, starting from A. At the end is L. So in this way, very simple integration, we get the answer. And this equal to delta K. Delta K, initially Ki is 0 because at the rest. So this is the final kinetic energy. V. V is the one we want to find. We do the square root, we get a V. That's the answer. Sample. Water area S 25 square meter and depth 1.5 meter in the well should be pumped onto ground 3 meters higher above the water surface. Find the work a pump have to do. We notice that water in different part of a well need different work to pump it out because the depths are different. So what we do, we divided this well, the water in the well, in many horizontal layers. Then the water in each layer need the same work to pump to the height. That's the trick we do. For example, if I take the reference orange on the surface of the well and downward as a positive direction, we look at this layer, horizontal layer. We pump this layer to the target place. The work done, d work done, it would equal to dm, the mass, gh, the h is, this is 0, so this is x plus big H, the small dw, okay? And the many layer put together, okay? dm, the mass of this layer equals the volume multiplied by the density of water. The volume of this layer is S dx. So we do the integration because the whole work is done by different layer. This is a sigma. Then we put this number dm into, we say this is dm equal to rho s dx, okay, plus the g plus the height. From where to where, with the layer we take from x to 0, go to this one, go to x equal to h. So integration limit is from 0 to h. Okay. Then we do the integration. I'm not going to do it. It's very simple one. We take constant out when doing integration. This is hx half x squared. So finally, we get the answer. Now, we put the number inside. This density of water, 1009.8 squared 25, h 3.0, small h 1.5, and we get the answer. We take two significant figures. We can do this one in different way. We take the different reference. We take reference orange at the bottom of the well, going up. So we will do it in a little bit different. You see this layer location at x, and this is h minus x. So the height of this layer to the top is big H plus small h minus x. We see how much work we have to then pump this water. As dm, the mass of this layer, gh. In this case, since we choose a different reference, the case how we count it, this is h minus x plus big X. So h minus plus big, the height, mgh. So dw is the work done to this layer to pump it to this level. Same thing, dm is mass equal to volume times density. The volume of this layer is S dx. Okay, we put everything inside. And this is the work done to this layer. We have to cover everything. That means x change from 0 to small h. So the total work done is integration. From where to where? From x equal to 0 to h. We put the dm in. Rho g s dx. But this is gh. Okay, integration is from x equal to 0 to x small h. Okay, we get the same answer. I'm going to do it.